Mason, and this is my Lab 5 on magnetic braking. Introduction and key concepts. In this lab, we'll be utilizing Newton's second and third laws, the magnetic field of a bar magnet, Faraday's law, and Biot-Savart's law. To do this lab, the first thing we must do is to find the magnetic north of the magnet. Then, you must measure the dimensions of the aluminum foil rod, the width of the foil, the length of the tube, and the total length of the inside of the tube. Then, to do the lab, you must drop the magnet through 6 times through the tube and measure the time it takes to fall through the tube. You will notice that the magnet seems to fall very slowly through the metal and aluminum. For measurement, we determine that the inside radius of the tube is 0.016 meters, the width of the aluminum foil around it was 3 millimeters, and the overall length of the tube was 0.3 meters. From our 6 trials, we determined that the average time it took to fall was 0.72 seconds, and our 6 trials are shown in this table below, with all the times being generally close together. Oscilloscope code for creating the computational model of the magnet falling through the tube. First, by creating putting our data points of the dimensions of the tube. Then, using this function right here, we're able to create the magnetic field from the magnet, and then we're able to determine the flux through each ring of the outside of due to the magnet function, and then able to determine the flux. The oscilloscope code was able to take the flux from what we determined, and then in this loop able to determine the magnetic force created by this and the current that is created using Biot-Savart's law and Faraday's law, and we were able to determine the speed of the magnet falling through the tube in the predicted model. On the right, this is a visual representation of the magnet falling through the tube. The red color shows that it is spinning clockwise, and if the magnet was flipped the other way around, it would be spinning. The current through the magnet would be going counterclockwise, and then it would become blue. From our experiment, we determined that it took on an average 0.72 seconds for the magnet to fall through the tube. Our predicted model showed that it took 0.789 seconds to fall through the tube. This is around an 8% error. This is very close, and some possible sources of error would be because the predicted model does not take into account air resistance, and also in the experiment there could also be inaccuracy in timing, and also the magnet may start with some initial velocity which would alter the time it would take to fall through the tube. Also, the graph shown also shows that it is a flat graph for velocity versus time that shows that there is zero acceleration of the magnet as it falls through the tube. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? This would change the speed of the magnet falling, because if the resistance went close to zero, the magnetic force induced of the magnet would become much higher, and the magnet would go very slowly through the tube. If it might not even fall at all if it is strong enough. Also, what if there were holes or slots cut in the tube? How would this affect the ring currents in your model? This would make the strength of the rings of current much weaker, and the magnet would fall much faster through the tube.